Good morning. Here I'm Sangeeta Lakshmi, working as assistant professor in EC department at R.M.K College of Engineering and Technology. Today we are going to see the some important topic in sequential circuit design. So we are going to see the dynamic latches and resistors. Actually, we have seen the static latches and resistors. Static latches are having some disadvantage. That is, it is very complex. That is, if you want to design the master slave um, static latch and resistor means what happened requires the totally it requires 20 transistors. Okay, if you want to design the master slave, it requires 20 transistors, whereas in dynamic latches and resistors it requires very less number of transistors. That's what we are going for here. The main difference between static and dynamic is in static it uses the positive feedback, so it requires the two cross coupled inverter in the positive loop, so it requires more number of transistors. Whereas in dynamics, it uses the capacitor associated with the transistor to store the data or hold the data. So here a dynamic resistor requires less number of transistors. That is the main advantage of dynamic latch. Okay. So what are all the types of dynamic resistor we are going to see under this topic is, first we are going to see transmission gate, dynamic transmission gate edge trigger resistor. Similarly, second one is C square mass resistor, and third one is PSCCR, that is true single phase clock resistor. So in this we are going to see the first two. First we are going to see the transmission gate based resistor. The dynamic transmission gate edge triggered resistors requires the two latches. Actually, the concept, whatever we are using in the static and dynamic, both are same. But only thing is there we have used the positive feedback. Here we are used the capacitor. That is the main difference. See here, this first one acts as the negative latch, right? The second one acts as the positive latch. Already we have discussed what is the difference between latches as well as resistor, and what is the difference between positive and negative. Everything we have discussed in the last class. Okay, so negative latch in the sense, you know that when my clock is 0, that time my output q equal to input, means it is called as negative latch. Then the latch is said to be in transparent mode, right? When my clock is 1, that time my q equal to q, that is it hold the previous data, means we can say the latch is in hold mode. This is the negative latch. Okay, whereas in positive latch, when my clock is 1, that time my output equal to input, so we can say the latch is in transparent mode. Similarly, when my clock is 0, that time q equal to q, that is it hold the previous data, we can say the latch is in hold mode. So if you want to design the register, means if you want to design the registers, we need two latches, right? First one is negative latch, second one is positive latch, means then it is called as positive edge triggered resistor. Okay, it is positive edge triggered resistor. Suppose if you want to design the negative edge trigger, means the first latch must be positive latch, second latch must be negative latch. That is the main difference between positive and negative latch. Okay, so here you can say the same concept. If first latches act as master, means the second latch act as slave. That means if the first latch act as in the transparent mode, means the second latch must be act as a hold mode. Slave should be hold and master should be in transparent mode. It is vice versa. See, when my clock is 0, I told you, no, when my clock is 0, that time my output equal to input, right? See here, my clock is 0, that time my input here is, for example, I'm taking 1, means when my clock is 0, this PMOS, here it is PMOS, it is NMOS. This is nothing but a transmission gate. Transmission gate 1 is nothing but a parallel combination of PMOS and NMOS. The advantage of using transmission gate is we can pass strong 1 as well as strong 0, right? So when my clock is 0, clock bar equal to 1. Thereby the PMOS, you know that if you are giving 0, the PMOS will on. If the input is 1, means definitely the NMOS will on, right? So PMOS and NMOS both are simultaneously on when my clock is 0. then we can say the transmission gate T1 is an on condition. So if it is an on condition, the data 1 will be passed on to the output side of the transmission gate. We are getting 1 here. This 1 will be stored by this capacitor C1. This capacitor is nothing but the capacitance due to this inverter I1, right? This is the gate capacitance of the inverter I1. See here, gate capacitance of the inverter I1, junction capacitance of the transmission gate T1. Junction means it is nothing but a diffusion capacitance. Diffusion means drain as well as source are called as diffusion, as well as overlap capacitance of the transmission gate, right? So these three capacitance, if you are adding, then you are getting the equivalent capacitance C1. Similarly, C2 also. This is due to the transmission gate overlap capacitance T2, junction capacitance of T2, as well as the inverter input gate capacitance I2, right? Okay. So when my clock is 0, that time the transmission gate 1 is on. During the same time, see here, when my clock is 0, I told you clock bar is 1. During the same time, see here, you are giving the 0 to the NMOS and 1 to the PMOS. Thereby this transmission gate set to the off condition. I already told you one should be on, another must be in off, right? The concept of master slave here. The first one is now it is act as the master, the second one act as a slave, right? So the C1 hold the next data, that is n plus 1th data, means the second latch will hold the nth data. It will hold the nth data and this will hold the n plus 1 data. Both should not collide to each other. That's why we are making only one latch should be on at a time. Okay, both should not be on at a time. If both are on, nth data as well as n plus 1 data, both will be collide to each other. Clear everybody? Okay. So this is the concept of dynamic transmission gate edge triggered resistor. Here we have to know how many transistors are required. See here, how many number of transistors are required to design our dynamic resistor is. See here, for transmission gate, here we are using two transmission gate. So two transmission gate means each transmission gate requires two transistors, so totally four. Similarly, we are using two inverters, right? So each inverter requires two transistors, totally here also four. So 4 plus 4, it requires 8 transistors. So it requires 8 transistors to design for this dynamic. So when compared to static, it requires 20 transistors, but here it requires 8 transistors. That's why I told you in the starting of the class, it is less complex when compared to static, right? And also, we can implement the same concept by using NMOS only pass transistor. Even we can reduce the number of transistors from 8 to 6 transistors if you are using NMOS only. Instead of this transmission gates, if you are using NMOS transistors, right? Here also, if you are using one NMOS transistor, what happens? You are removing the two transistors, one from T1, another one from T2. Thereby, instead of 8 transistors, it requires 6 transistors. Okay, so this kind of um, dynamic latches is preferred in the or attractive in the high performance as well as low power system, right? And one important thing we have to know is this is the dynamic latch. So I already told you it is stored using the capacitors. So this capacitors can capable to store the data for a certain amount of time. So after that, the data which is stored by the capacitor will be lost due to the charge leakage, diode leakage, as well as subthreshold current. So due to that, the data will be reduces, that is the stored data in the capacitor will be changes. Okay. So periodic refreshment is required to hold the data. But the refreshment is not an issue, especially in data path circuit. Right? Okay. Next, we are going to see what is the impact of non-overlapping clock. See here, we know that the clock and clock bar, they are used in our design, right? So how to generate the clock and clock bar is definitely if we need the inverter. If you are having clock at the input, you will be getting the clock bar at the output. So whenever my clock is changes from 0 to 1 means clock bar has to change from, it is 0 to 1 means it has to change from 1 to 0, right? That means clock and clock bar must be complementary to each other. But these two will not produce at exactly at the same time, right? It is the ideal case. It is not at all possible. You can see here when my clock is changing from 0 to 1 to 0, that time my clock bar will change from 0 to 1. But both will not change at the same time because of this propagation delay of the inverter, right? So during this small interval of time, what happens? The clock is 0, clock bar also 0. This is called 0-0 overlap. Similarly, you can see in this small portion, my clock is 1 here, my clock bar also 1. So this is called 1-1 overlap, right? I already told you if you want to make the master slave concept that we are using the clock and the clock bar because one latch is in the transparent mode, another must be in the hold mode. That is a master slave concept. So that's why we are using the clock signal. But if you are using clock and clock bar in the same circuit, what happens? This will make 0-0 overlap as well as 1-1 overlap. So due to that, what happens? This small amount of time, both latch will be goes to transparent mode or both latch will goes to hold mode. That is not the desired, right? That is not desired one. So we have to take these some special measures to design our dynamic latches in order to overcome this um, clock skew. That is, this 0-0 overlap as well as 1-1 overlap will make the race condition. Okay, so race condition means if both the latches are on means what happens? One latch is holding the data of n plus 1, another latch is holding the data of nth data. If both are on means nth data as well as n plus 1th data will collide each other, right? So um, the next circuit will fail to take the data either nth data or n plus 1 data. It has some racing. So this is called race condition. Okay. So this is due to the clock skew. Clock skew means uncertainty in the arrival time. The clock and clock bar will not change at the same time, right? This is called clock skew. So next we are going to see the C-square mass which will be insensitive to clock skew. See the C-square mass means clocked C-mass, right? See this is called as clocked C-mass. See, clocked CMOS is insensitive to clock skew. Clock skew means I already told you uncertainty in the arrival time. That is, my clock is changes from 0 to 1 means I am expected that the clock bar has to change from 1 to 0 at the same time, right? But it is not a practical case, it is idealistic case. So due to that, what happens? We are getting the 0-0 overlap as well as 1-1 overlap for some duration of them. So in this period, what happens? Both the labs will goes to either transparent mode or hold mode, but this is not desired operation, right? So to even though the 0-0 overlap and 1-1 overlap is coming, the circuit must be vulnerable to clock skew. That is, it should be insensitive to clock skew. So in such a way that we have to design the register. So here we are going to see the C square mass, which is the big solution for this problem. Okay. See here we are using the tri-state inverter. Tri-state inverter. This is nothing but the tri-state inverter. Tri-state inverter acts as the tri-state inverter act as the inverting latch. Okay, it is act as the inverting latch. Inverting latch. You know that latch means what? For example, negative latch if you are taking, what happens when my clock is 0, that time my output equal to input. Here my input is D, my output is X. Okay. So here X equal to D bar. It is inverting latch. I told you no, when my clock is negative 0, my output equal to inversion of input. Okay. So this is called negative latch. See how, first of all, we have to know what is this tri-state inverter. Normally, inverter means you know that the inverter having the one PMOS and one NMOS, right? So if you are giving the input A, you will be getting the output as Y. So if you are giving 1 here, you will be getting 0. If you are giving 0, you will be getting 1. So this is the inverter. So you can able to get the two outputs. But tri-state inverter means in addition to 1 and 0, we will get another output which is called as high impedance state. How first of all we are going to see that. When my clock is 0 and the clock bar is 1, that time M4 is on, M3 also on. Depending upon my input, for example, my input is D equal to 1 means this transistor will goes on. So you will be getting output equal to 0, right? So see here, when my clock bar I'm having, clock is 0, clock bar is 1, that time my output equal to X equal to, if I'm input is 1, you will be getting 1. Sorry, my output is 0 because here you are giving 1, you are getting the 0. Similarly, if you are giving input is 0, my clock and clock bar is 0 and 1, you will be getting inversion here, so it is 1. Suppose even though my input is 1 and 0, my clock is 1 slash 0 means what happened? Both the M4 and M3 in the off condition. That time my output is not connected to either supply VDD or ground. So we can say the X node is in the open, that is high impedance state, open circuit. Okay, that's why in addition to 0 and 1, additional output we are having high impedance state. It is called as tri-state inverter. Okay, three states we are having. Okay, this tri-state inverter can act as the latch, inverting latch. Okay, see here, the first one is negative latch, the second one is positive. Here we are giving clock signal, but here we have given clock bar, right? See, when my clock is 1, right? When my clock is 1, the clock bar is 0, thereby this on, this is also on. See, this 0 will be connected to M6 as well as M5. The 0 will make this M6 transistor on, so that you will be getting output equal to what? The output equal to 1, right? So, this is the operation of C square mask. So first one is act as master means second one act as a slave. First one act as slave means second one act as a master. Okay. So this is the concept of C square mask using master slave concept. So it is insensitive to clock speed. How we are going to see that? See here, when my input is, that is 0 0 overlap, next we are going to see 1 1 overlap. 0 0 overlap means when my clock also 0 and clock bar also 0. When clock bar is 0 means what happened here? We have one transistor, right? This is NMOS transistor. You have given 0. 0 means definitely it is an off condition. That's why this is disconnected from the circuit. Okay. But because of this 0 here, this M4 will goes on. Okay. Then if the input is 0 means what happened? M2 also on. So this path is closed. The X equal to 1 because VDD equal to 1. This 1 will make this M5 on, right? Here also we have one transistor NMOS, that is also you have given 0 because the 0 0 overlap, clock and clock bar all are 0. See the previous circuit. So this is off because of 0 at the gate. That's why we have disconnected from the circuit. Okay, but this M8 transistor will goes on, but this one will not make this M6 on, it is also an off condition. So now you can see this first one will first latch act as the transparent mode, but second one is the hold mode. That hold, how we are saying this hold means the output is not connected to supply or ground. Any power supply line, it is not connected to the output side, so it hold the previous value. That's why the second one is act as, we are saying that this in hold mode or it is slave, right? The first one act as in master, that means it is in the transparent mode. Similarly, you can see 1 1 overlap. 1 means clock and clock bar all are 1, right? See, in the previous circuit, you have to apply all clock and clock bar is 1. See here, you have here one PMOS transistor, right? Here it is 1. 1 means it is off condition. That's why we have disconnected here. Here also, we have one transistor, right? Here also 1. That's why we have disconnected this. Okay. So, because of this one, M3 is on. If my input is 1, M1 also on. So, this path is closed. X equal to, you will be getting 0 because X is connected to the ground, right? So, this 0 will be make this M6 transistor on, right? But the M5 is in off condition. Even though the M6 is on, the output is not connected to VDD because of this disconnected transistor. It is in off condition. Similarly, this Q is not connected to ground terminal because of this M5 transistor in off condition. Thereby, this first one acts as the master because the output is connected to the either supply or ground. That means it is transferring the data from input side to output side. So we can say this first one acts as the master, that is in transparent mode. The second one, output is not connected to either supply or ground. That means it is not transferring the data from input side to output side. So we can say this latch acts as the slave. That means it can preserve the or hold the data which is in the previous value. Okay. So this clearly explains that during 0, 0 overlap as well as 1, 1 overlap, the C square mass is insensitive to clock skew. Thereby we can avoid the race condition from this circuit. Thank you. With this I hope that everyone understands this. Thank you.